It has to do with curiosity. It has to do with people wondering what makes something do something. And then to discover that if you try to get answers, that they're related to each other. That things that make the wind make the waves, and the motion of water is like the motion of air, is like the motion of sand. The fact that things have common features turns out more and more universal. What we're looking for is how everything works, and how everything is, what makes everything work. And what happens first in the history is we discover the things that are on the face of it obvious. And then gradually that we ask more questions, and then we dig in a little deeper to things that we can just make. We need to do a little more complicated experiment to find out about it.
I like that a lot. Like, crop circles in secret are actually luminous at night. Here we discover them as the nebula part, and we present the name of our guest. And here we are, live.
Good evening, I'm Sunny Shell, and this is The Crucible on the Promethean Secular Frontier, where we discuss science, philosophy, and reason from a secular perspective. And I'm really excited because tonight we're going to be discussing dark matter, dark energy, and why they matter with one of my absolute favorite guests on The Crucible. Hello, Ethan Siegel. How are you doing?
Hi, it's my pleasure to be here. Thanks for having me back. And you're talking my language. This is some of my favorite stuff to talk about. So dark matter, dark energy, the invisible universe, oh man, we are in for a treat tonight.
I'm excited. So for anyone who is a new viewer to PSF and to The Crucible, could you let everybody know your background? Tell us a little bit about you.
Sure. My name's Ethan Siegel. I'm a theoretical astrophysicist. I have been a PhD researcher in theoretical cosmology. I've held positions as a research associate and a professor at a few different colleges. But I stopped teaching in 2015, and I've been focusing on science communication. I write the world-renowned blog Starts With a Bang, currently hosted on Big Think. And you can find me, Starts With a Bang, on Twitter, Facebook, SoundCloud. I have a podcast, Patreon, where you can support me, and I know folks can support you in Promethean Secular Frontier as well there. And that's my deal. You want any more info about me? Check me out at startswithabang.com, and that'll take you everywhere you need to go.
And I will say I love Starts With a Bang. It is fantastic. So y'all need to check that out. So, okay, let's just dive right in. I want you to tell me, what is dark matter?
Oh man, I want to know what is dark matter, because if I knew, and I knew how to tell you to prove it to yourself, not only would I win the Nobel Prize, but I would solve one of the biggest open questions in all of physics today. Dark matter is matter, massive matter that's out there in the universe that interacts gravitationally on the largest cosmic scales. It's responsible for the large cosmic structures that's formed. It's why galaxies stay together. It's why groups and clusters of galaxies clump together as they do. It's why we have this filamentary structure on the largest scales called the cosmic web. But it's also very difficult to detect, because as far as we can tell, it doesn't collide or interact with normal matter, with itself and other forms of dark matter, or with light. So we call it dark matter, but really it's invisible matter. It's matter that has mass and gravitates, but doesn't clump or cluster together. It makes up about 5 times as much of the universe as all of the normal matter combined, and we can detect it indirectly through its indirect effects. We know it's there, and I imagine we're going to talk in gory detail about how we know it's dark matter and not some other thing. But we're really, really confident that it's out there. What we don't know how to do is how to detect it directly, like how to detect it the way you detect other particles by smashing together in the lab, or like you would detect light with like a telescope, or how you would detect gravitational waves with these giant interferometer arms that move as a gravitational wave passes through. How to detect dark matter? There are a lot of efforts being made, but no one has said, there's your smoking gun. That's dark matter.
Well, okay, that's interesting. I know that the way we first kind of figured out what dark matter was in seeing how the universe was expanding and continuing to expand, and we couldn't figure out why. Is that correct? That's how we first kind of started figuring out what that there was something called dark matter?
You flipped them. That is dark energy. We're
Gotcha.
talking about dark matter. They're two different things. So something that acts like matter is going to clump and cluster together. The big difference between dark matter and dark energy comes as the universe expands. So I want you to imagine that you've got a universe like ours that's full of stuff, atoms, molecules, light, all the stuff you know. What happens as the universe expands? The volume of space increases, but the number of particles in the universe stays the same, right? If I have like a balloon, right? If I have a balloon and I tie off the balloon and I take the balloon into space, the higher up in the atmosphere I go, the less pressure gets exerted on the outside of the balloon, and so the balloon expands. But the number of particles in the tied off balloon stays the same. That's what happens to matter and radiation in the expanding universe. The volume increases, but the number of particles stays the same. So as the universe expands, the density goes down, because density is mass over volume, or number density is the number of particles over a volume. The volume expands, the number of particles stays the same, so the density drops. With dark energy, that's something entirely different. That's saying we think that there is a certain amount of energy inherent to space itself. You have this vision like, I know what nothing is. If I took this box or region of space and I took everything out of it, right? No air, no atoms, no molecules, no dark matter, no nothing. I took everything out of it. What would I have? I'd have nothing, right? No, wrong, of course, right? Why would things be intuitive? It turns out that what we call the 0 point energy of empty space, the amount of energy that's left over in space if you take everything out of it, is not 0. It is a finite positive value. And the reason we think that this is the case is because there are certain things that you cannot remove from space, like the quantum fields that underlie reality, like the forces of nature, like the laws of physics. And you're like, why would we know that this is something that's actually real and has energy? And the answer is, we got a huge clue because there was an experiment that was done to show us something called the Casimir effect. If I take two parallel conducting plates, right? You know, if you've ever messed with a conductor, that electricity flows through a conductor very easily, right? That's what you use conductors for. You make wires out of them: gold, silver, copper, aluminum, all really good conductors. You make wires out of them. You can do all sorts of things that are very interesting with conductors. And if you're watching this on YouTube right now, you're probably doing those things too. You're probably taking advantage of those conductors. Well, if I have two parallel plates, two parallel conducting plates, what happens? I would say, okay, let me evacuate the chamber that they're in. I'll put them in a vacuum chamber so there's nothing else in there. what else is going to be in there if I take everything away? Well, I'll still have those fundamental quantum fields that are inherent to space that I can't get rid of. Now, here's where it gets interesting. Outside of the plates, these waves, these fluctuations, they can come in any wavelength, right? I can have waves that are tiny with short wavelengths. I can have waves that are big with long wavelengths. They can all exist throughout space. But what about in between those conducting plates? When I have two conducting plates, all of a sudden I have what we call in physics boundary conditions. I can only have specific sets of wavelengths, like standing waves, that can exist between these 2 points. Just like if I take a guitar string, a taut guitar string, and I pluck it, yeah, I can put my finger down on various places and have it make different notes. But as long as I have that string pinned down at 2 points, there are only certain types of waves that can exist on that string. Well, if these quantum field theoretic waves, if quantum field theory had, bam, energy to it, if these fluctuations had energy to it, then I would say, oh no, look, I've got all these different waves that exist outside of the plates, but I only am allowed to have a subset of those waves in between those plates. So what I would expect is there would be more energy outside of the plates, less energy inside of the plates, and that would cause the plates to either attract or repel depending on the value. So if the plates stay constant and there's no force between them, then I can say, okay, these things don't have energy. But if the plates accelerate this way or accelerate this way, then I say, ooh, I have a real effect there, and there is some sort of energy inherent to the fabric of space itself. And guess what? Casimir theorized this in the 1940s. And about 50 years later, a scientist named Stefan Lamoureux measured it. And we know, oh, shoot, these plates really do move. These plates feel forces. And the Casimir effect is real, it's physical. And in concert with dark energy, are these two related? Maybe, we don't know how. But are these two things related? Well, we see the same thing in the universe. Dark energy on large cosmic scales, you take gravitationally unbound objects, and they're not only expanding with the expansion of the universe, but this expansion is speeding up. If I watch a distant galaxy from where I am, and I see this galaxy move away from me, and the universe expands and it moves away from me, guess what? Over time, it moves faster and faster and faster. And that's what we mean when we say the expansion of the universe is accelerating. And what drives the expansion of the universe? That's what we call dark energy. So that's different than dark matter, which has mass and clumps together. And as the universe expands, dark matter gets less dense, just like regular matter does. But dark energy, you expand the universe, now you have more space. The energy density remains constant. So think about that. If density is mass over volume or energy over volume, and that's staying constant, then as your universe expands and your volume goes up, that means the total amount of energy goes up. So dark energy is getting more and more intense. There is more energy in the universe now than there was at the start of that sentence. And by the time you finish your next sentence, there'll be a little more dark energy in the observable universe then than there is right now.
That is absolutely so cool. That was actually what my next question was going to be, was how, what is the difference between dark energy and dark matter? And by making that mistake, I was able to go right into that. So that's really cool.
I love this attitude, by the way. Like, we all make mistakes. That's how we learn things, right? If you knew everything coming into this program, you wouldn't need to have me on. You would just talk for however long you wanted to talk for. But that's why you have someone on who studied this, who knows about this, because you say, okay, sometimes I'm going to have misconceptions that I don't even know I have. What misconceptions do I have? And the difference is dark matter and dark energy. For dark matter, It's massive, it's clumpy, but it's invisible. For dark energy, we think it's everywhere, it's inherent to space, and as the universe expands, you have more space, you have more dark energy. That's why, by the way, if we were born like 8 billion years ago, way early on, a little more than half the universe ago, we wouldn't know about dark energy. It would be too small for us to measure it. It's only once the universe expands and gets dilute enough that the matter density, normal matter, dark matter, that energy density drops below a certain amount that you can actually detect dark energy in the first place. So we're kind of born, we kind of exist at this amazing time where we can see all the way back towards the early stages of the hot Big Bang, and we can still know this low energy, dark energy that's present, that's going to drive the fate of the universe. So we can see the beginning, we can see the end, and we can see a universe right now that's full of stuff. 10 billion years in the past or 100 billion years in the future, neither one of those would be the case. We would be limited.
That's interesting. So I want to go back to my first question then, or what I was actually alluding to. I now know how dark energy was first detected. How did we first know about dark matter? How was that first brought?
Dark matter, it depends who you ask, because you can get one of two origin stories for dark matter. So the first origin story for dark matter goes all the way back to the 1930s. And there was this scientist named Fritz Zwicky. And Fritz, in 1933, was observing galaxies around the Coma cluster. Coma is a constellation in the sky, and in the constellation of Coma, there is a big cluster of galaxies. How big? It's got about 3,000 Milky Way-sized galaxies in it. It's really big. It's a few 100 million light years away. So it's kind of far, but it's close by relatively compared to the scale of the universe. So for its distance, the Coma cluster is the biggest, most massive cluster within that distance. And what Fritz Zwicky was doing was extremely clever. What he was doing was he said, okay, I can infer how far away these galaxies in the cluster are. And I can infer, based on this distance to them and how much they're separated by, I can infer how far apart they are for one another. I could say, like, okay, these two are separated by about 5 million light years, and those two are by like 7 million light. So he could figure that out. And then he said, oh, but there's another piece of information I can measure. When these galaxies zip around in space, right, they're like stars in our own galaxy or planets in our own solar system. They orbit each other. They're gravitationally bound together, and they swarm around, they move. Well, you can't measure for an object really far away. You can't measure how it moves side to side or up and down, but you can measure how it moves away or towards you. Because if something is moving towards you, then when it emits light, because it's moving towards you and it emits light, that light is going to have its wavelength compressed. It's going to be what we call blue shifted towards the bluer end of the spectrum. Just like when you hear an emergency vehicle or an ice cream truck moving towards you, it's higher pitched. And then when it moves away from you, it's lower pitched. Well, when a galaxy moves away from you, its light is shifted towards the red part of the spectrum, shifted towards longer wavelengths. So that's what he was doing, is he's saying, okay, I can measure these individual galaxies within the cluster, and I can see both relative to us and relative to the other galaxies in the cluster, how fast are they moving? And based on how fast they're moving, because if they're gravitationally bound together, how much mass has to be in there. So Fritz Zwicky said, okay, I'm going to measure how these things are moving. I know the scales of it, and I measure the speeds, so that'll tell me how fast the galaxies are moving. And I'll get a value for how much mass has to be in this galaxy cluster. And then he said, oh, but guess what? We're astronomers, right? So we know how stars work. And when we measure starlight, we can calculate how much matter, how much mass is there in all the stars. So if, he said, we understand how this works, right? If we understand, okay, galaxies are made out of stars and stars dominate solar systems. So when we measure all the light, we should get a value for how much mass is there in stars. And then when we see these things moving around, zipping around, we get another value, how much mass is in the cluster total. If in a dream world that stars made up all the mass, then these two numbers would match. That's what Zwicky said. But not only didn't they match, they weren't close. There was more mass total from the moving galaxies than there was in stars by a factor of about 160, according to Zwicky's calculations. Now, this is way back in the 1930s. So people had all sorts of objections back then. They said, okay, number one, what makes you think all stars are like the sun? What if there were stars out there that have different mass to light ratios? And what if the sun isn't typical? So maybe this factor of 160 is because stars don't work the way our star does. What do you think of that, Fritz? Then they said, okay, guess what? It's not just stars. Sure, stars dominate our solar system, but maybe there are lots of planets around out there. Maybe there's gas, maybe there's dust, maybe there's plasma, maybe there's lots and lots and lots of normal matter that isn't in the form of stars. And so people were like, Fritz Zwicky, yeah, you know, he's crazy. He's out there. He's out of the box. Let's ignore him. The thing is, people who said that were right, but not by enough. It turns out, yeah, other stars are different, even on average, than our sun is. But if you account for that, they're only about 3 times more luminous on average than our sun is. So that takes you down from 160 to 1 to about 50 to 1. But that's still lousy. That's still a huge mismatch. And then you say, okay, well, look, stars aren't everything there is. There's plasmas and gas and dust and planets and maybe mini basketballs out there and all sorts of other clumps of matter. And that's true also. And that takes you down from 50 to 1 to about 6 to 1. But that's it. That's everything. So it turns out there's much more mass out there than all of the normal matter combined can account for. This got revitalized 40 years later in the 1970s as Vera Rubin and Kent Ford started measuring individual galaxies. The equipment got good enough that when you see a galaxy, right, a lot of us think of these big, grand spiral arms. These, you know, you got a big center of the galaxy and then these arms spiral around it. And there's multiple arms and they spiral around it, they spiral around each other. And that's that beautiful structure. You can see that when galaxies are face on to you, right? You can see their structure. But what about when galaxies are edge on to you? Well, you can't see the spiral structure as well. Maybe if they're like this, you can. But what you can see is if this galaxy rotates, then part of this galaxy is rotating towards you. And the light on this side of the galaxy will be blue shifted because it moves towards you. And the light on this side of the galaxy, because it moves away from you, is going to be red shifted. So what they decided to do and what they were able to do is they were able over different parts of the galaxy to measure how fast is it rotating. And what you expect if there's no dark matter, if the normal matter, what you see is what you get, is things would behave like the solar system, where the inner planets orbit real fast because they're close to the sun, and so there's a lot of centripetal acceleration, and the outer planets, no, they move slower. The outer planets move more slowly because they're farther away. The gravitational force is less, so the centripetal acceleration is less. In our solar system, Mercury is the fastest planet. It moves at almost 50 kilometers a second around the sun. Venus is slower. Earth, we're more like 30 kilometers a second. You go farther and farther out, every planet slower than the last until you get to Neptune, which is only about 5 kilometers a second around the sun. But guess what? When we started looking at other galaxies, we found like, okay, in the inner regions, you get these fast moving stars. They go around their galaxy like 200, 300 kilometers a second. And as you move out, what happens? The speed stays the same. It doesn't drop. And that tells you, oh, now I have this huge reason to believe there is some extra mass, some extra matter there beyond the normal stuff that I know is there. So that was our first, I'd say, robust, our first, like, everyone's now taking these observations seriously, evidence for dark matter. I always wonder, you know, if we had taken this seriously 40 years earlier, because he was right, like he was correct, could we be 40 years closer towards our goal of solving this dark matter mystery? Did we just ignore it when we should have been paying attention? And the answer to that is, we probably wouldn't be 40 years closer, but we'd probably be closer. And, you know, it just goes to show that when you get observations that, you know, don't line up with your theory, don't discount them immediately. They may be hinting at something that's really worth paying attention to.
There's also the point to be made to always be skeptical, because just because something is said within science doesn't mean that it necessarily is reality. So it's always good, and that's one of the great things about science, is that you have to be able to test and make some type of predictive. It has to have some type of prediction that you can measure from that, if I'm making sense.
I think you're making great sense. Should I explain it back to you in my own words to see if you make sense?
Absolutely.
So what I would say is, look, when I say these galaxies are rotating at a different, you know, with a different profile than I would expect, the skeptics out there are immediately going to say, well, what else could it be? Does it have to be dark matter? Could there be some other way to look at it? And the answer is, yeah, it could be something else. We could instead, what if we said, oh, you know what? What if we got the laws of gravity wrong? We think Einstein's general relativity is like, it rules the whole universe, and it works really well on all these different scales. But what if it messes up on galactic scales? What if we need to change the law of gravity? It turns out that for individual galaxies, you can change the law of gravity by modifying it and saying there's some minimum acceleration that you can never drop below. And if you try to drop below it, like whatever is causing that minimum acceleration is going to keep you there. And that's why these rotation curves stay flat and at such a high speed when you move farther away from the galactic center. Now, that's when you get to your point of saying, okay, so now you got two ideas that could possibly explain this weird stuff you observed. So if we had dark matter, what would be the consequences for the rest of the universe? Versus if you change the law of gravity in this way to make them work for individual galaxies, what would be the consequences for other things in the universe? And that's why it's when we ask that question that we think dark matter is so important, because all of a sudden you say, okay, well, let's look at those galaxy clusters, right? The ones from Fritz Wiki, and also like observations have come a long way in the last 89 years. So we've got a lot more now. So when we look at these galaxy clusters and we see how the individual galaxies move in them, what happens if we try to make the same modification to the law of gravity that we made for individual galaxies? The same modification doesn't work. You would have to throw in a different modification on top of the one you made to explain galaxy clusters. And then you'd say, okay, well, what about the cosmic web and the large scale structure of the universe? And if you said, okay, well, I worked with modifying the law of gravity and I made the modification for galaxy scales and I made the modification for cluster scales. Now, what do I need to get the large scale structure? You have to make another modification. And this time, your modification needs to look a whole lot like dark matter for it to work. Then you can look at the cosmic microwave background, the leftover glow from the Big Bang, and say, oh, guess what? In the very early stages of the universe, what happened? I had matter that tried to collapse, but I had a bunch of radiation early on. Things were hot. It was not just the Big Bang, it was the hot Big Bang. Things were hot back then. And you know why? Because the universe was smaller. Radiation has a wavelength. So if the universe was smaller, the wavelength of the radiation was smaller, and small wavelength radiation is hot, and long wavelength radiation is cold. So back then the universe was hotter. So, okay, great. So universe tries to collapse. It's hot. The radiation pushes back against it. So I should see on different angular scales corresponding to different physical size scale, I should see these bouncy features in it, where I would say, let's look at the universe's temperature, and there should be a peak and then a valley, and then a peak and then a valley, and then a peak and then a valley, and so on. And you can say, okay, well, how many peaks and valleys do I expect? And the answer is, it depends. Do you have a universe with dark matter in it, or do you have a universe with no dark matter in it? Because in a universe with no dark matter in it, you only get half the number of peaks. And in a universe with dark matter in it, you get twice as many peaks, because you have the normal matter that oscillates and pushes back and oscillates and pushes back. But the dark matter, because it doesn't directly interact with light, is going to interact and push back differently. It'll be out of phase, so you get twice as many peaks and valleys. When we do this, and we've done this since the late 90s, early 2000s, again, you would need yet another modification to modified gravity to explain these peaks and valleys. But dark matter is remarkable because of this one ingredient. You add it and it can fix all of these problems. But the nail in the coffin that I haven't even gotten to yet is we know exactly how much normal matter there is in the entire universe. Because in the very early stages of the hot Big Bang, when the universe was between a few seconds and a few minutes old, things were so hot that you could not make even an atomic nucleus. Things were too hot to take protons and neutrons and bind them together. Because as soon as you did, as soon as you're like, oh, I'm going to take a proton and a neutron and fuse them together and make a deuteron, the building block of all heavier matter to come is deuterium, one proton and one neutron bound together. Deuterium is very easy to destroy. You can make it, smash proton and neutron together, boom, deuterium. But if a photon comes along, a quantum of energy, and that has more than 2.2 mega electron volts of energy, it's going to split that deuterium right apart. So you have to wait. From the early stages of the universe, you have to wait for it to expand and cool, expand and cool, expand and cool, until you have few enough high energy photons that you can form deuterium without immediately destroying it. Astronomers who study this call this epoch, this time period in the early universe, the deuterium bottleneck, because the early universe is hot and dense. It's got like similar temperatures to the inside of a star. Less dense by the time you get to form these things. But anyway, so you make deuterium, and then you're like, okay, thankfully, I made deuterium. Let's now, bam, deuterium, protons, neutrons, smash them all together. What can I build up? Guess what? If you did it early on, early enough on, you would get a certain ratio of elements that you would have formed through nuclear fusion before any stars were made. The fewer, the less the amount of normal matter you have, or the more the amount of photons you have for each particle of normal matter you have, that changes the ratios. So you can ask, how much hydrogen do we have in the pristine gas that's out there? How much deuterium? How much helium-3, helium-4, lithium-7, other elements? based on those observations and those calculations. This is one of the great marriages of theory and experiment, or theory and observation. We can say, overall, I know exactly how much matter, how much normal matter, how many protons and neutrons there are all throughout the universe. And then I can compare it to, okay, and from our observations, from cosmology, from the large scale structure of the universe, from all that we see out there, how much total mass is out there, doing basically the same thing Fritz Zwicky did, but on a cosmic scale. And you get that when you take the total amount of normal matter versus the overall amount of matter that has to be there, this is only about 1/6. And the total amount of normal matter is 6/6. So that tells you that for every whatever kilogram of normal matter that's out there, you have to have about 5 kilograms of dark matter out there. So it's not like you got one piece of evidence and you're like, well, it could go this way or this way, and we think it's this way. It's like, no, we have all these different independent lines of evidence. And for this one line of evidence, if that was all you looked at and you put blinders on to everything else, you can say, okay, it could be either of these two. And maybe even this modified gravity one works better for this one example. But then you look at the full suite of everything you have and you go, oh, God, no. The modification that I used, it doesn't work for anything else. We get a galaxy cluster, and a galaxy cluster, we can watch them in the process of colliding together and passing through each other. Guess what? When you look at what happens, you can see all the gas in there. The normal matter that makes up the gas, it gets stripped out of the colliding galaxies. And what it does is it heats up and emits X-rays right in the middle. But then you look at, okay, but I know how mass works. And I know that when I have a massive clump of matter, it's going to act as a lens, as a gravitational lens, because it's going to bend space around the light. So that light from background objects is going to appear bent around wherever the mass is. So where's the mass? Is it in the middle with the gas? No, it passed right through, just like you expect dark matter to. And so the same modifications that would fix individual galaxies, if you said that's the cause of gravity, that's the cause of why galaxies rotate as they do, they don't work for anything else on large cosmic scales in the universe. So there are still people who work on this, but they're about like a 1 in a few hundred minority among astronomers. And I think for very, very good reason, because like you said, you make new predictions. You go out and you test them. You test the possible alternatives against the predictions you make. You look at the observational or experimental results of what's out there, and then you draw your conclusions. This is still obviously an open area of research, and it will remain an active area of research until we discover what sort of particle is responsible for dark matter. What properties does it have? How do you make it in the lab? How do you detect it directly? When we can do that, then we'll say, okay, finally, we understand it. But in the meantime, you're talking to me at this intermediate time where we know that there is some sort of extra matter out there. It has all of these properties consistent with the theory of dark matter, and it's inconsistent with just saying, let's modify gravity. But I can't tell you everything I'd want to tell you about it because we've only detected its effects. We've detected it indirectly rather than directly. And in physics, indirect detection is great. It teaches you a lot. So that's why, as someone who studies this, I say dark matter is definitely real and it's definitely out there and everywhere in the universe. But you say, and what's it made out of? I have to throw up my hands and say, not today.
Well, that just gives us more stuff to think about. So I do want to ask or bring some of the questions in that the audience has been asking the viewers because they have been kind of lighting up. So the first one that we have is from George Hamilton. Have you read the recent paper titled The Big Bang, CPT, and Neutrino Dark Matter? And if so, do you plan to write about it?
Okay. Oh boy. So there are all these papers that make splashes once in a while, and normally what I do is I at least read the abstract so I know what they're talking about. And this paper said, okay, first off, neutrino dark matter. Neutrinos are a perfectly reasonable dark matter candidate. The neutrinos that we have in our universe, right? They come in 3 flavors, and they're both made early on in the hot Big Bang and produced in stars or any place where you have nuclear reactions. Neutrinos are the second most abundant particle in the universe behind photons, and they're all over the place. When you say the neutrinos that we made in stars and that we made in the Big Bang, could they be dark matter? The answer is no. The reason the answer is no is because we not only have all of this matter out there, but we know that at some point, right, these particles, they started moving slowly compared to the speed of light. If things move fast compared to the speed of light, they act like radiation, not like matter. So we call it dark matter and not dark radiation because while radiation, can move really fast, what it can't do is clump together and form stable structures. So if you want matter to clump together and form stable structures, it has to move slow compared to the speed of light. And what we call that is cold. If you move slow compared to the speed of light, you're cold. If you move fast compared to the speed of light, you're hot. Neutrinos, as we know them, would be an example of what we call hot dark matter. But the dark matter we have in our universe needs to be cold. So neutrinos, normal neutrinos, can't be that. But there could be more neutrinos out there than we know of. There could be, all the neutrinos we know of are left-handed, which is to say, if you point your left thumb in the direction of a neutrino and you look at the way your fingers curl around your thumb, that's always the way the neutrino will be spinning. Neutrinos will always spin this way. And antineutrinos, their antiparticles, are all right-handed. Why are there no right-handed neutrinos? Why are there no left-handed antineutrinos? The idea is that maybe there were. Maybe at some high energy time early on in the universe, you had both left-handed and right-handed neutrinos, that they were symmetric and some sort of symmetry broke. Well, if that happened, then you could have heavy right-handed neutrinos, and that could be cold dark matter if you just had the right number of them. So that's the original idea of neutrino dark matter in the modern era. That is a good idea. But what this paper said is, okay, let's imagine that we have our universe where time runs forward, and there's another universe where time runs backwards, and one of these has certain properties and the other one has the opposite properties, and maybe they're connected somehow, right? There's like 8 different what ifs that this paper goes into to say, okay, like you have the anti-universe where time runs backward, and maybe that couples to this universe, and that solves all our cosmic problems. And that to me is pink fairy unicorns and Russell's teapot type of things where, yeah, I can't rule them out, but come on, like building a model where you have like a handful of new free parameters that you introduce and tinker with is way less compelling to me to say, oh, by the way, if you add dark matter to your universe, it solves all of these problems on all of these scales. So I'm not saying that like I think this idea about neutrino dark matter and CPT violation and another Big Bang in another universe, I'm not saying it's impossible. I'm saying when I look at that, I don't find it compelling. And if I don't find it compelling, it either needs to be like a global phenomenon that's everywhere like wildfire that needs some common sense talked into it, or there needs to be some big reason for me to come along and pluck this idea out of obscurity just to smack it down. I don't want to do that. So I have looked at the paper. I haven't read past the abstract, and I doubt I will because, it's old computer science gigo, right? Garbage in, garbage out. I'm sorry to the researchers who did this. If you're listening to this, I didn't mean to call your work garbage. I instead will leave you with the inspirational message that we all get one life, and you are free to spend yours studying and researching whatever it is that interests you, no matter how interesting or disinteresting I or others find it.
That was brilliant. I love that. You can actually do that. I mean, I've never met anyone who can say things like you do. And I'm just sorry, but that was just brilliant.
Well, if you want my inspiration, you can watch Denethor from the Lord of the Rings when he releases Pippin the Hobbit from his stead, and he tells him, "Now go off and die in whatever way you deem best."
Yeah. All right, the next one isn't exactly a question, but it kind of sparked a little bit of a discussion. So it said, I think this idea that one day you will have a black sky because everything's so spread out is damn shocking. How could they do astronomy? The science would be inaccessible. So my question to you is, would we even have life at that point? Would anything actually be able to, even if it's just a tree, would there be any, not just sentient beings, but would there be any life at all once it gets to that point where things are so spread out like that?
It depends on how spread out they are. It's not that long ago, we didn't discover that there were objects outside of the Milky Way until just under 100 years ago. It was in 1923, for the very first time, that we were looking at Andromeda, the Andromeda Galaxy, which at that point was not known as the Andromeda Galaxy because the Milky Way was the only known galaxy in the universe. They were looking at the nebula in Andromeda, and they discovered for the first time, oh, look at that thing that's getting brighter and fainter. That's not a star going nova and flaring up. No, this is a variable star that gets brighter and dimmer and brighter and dimmer, oscillatory with time. It was by measuring that and how the brightness changes that we were actually able to say, oh, I'm going to measure the distance to this. And we found that it was like not hundreds or thousands of light years away, but like 1 million light years away. I think the number that Edwin Hubble first got was like 0.9 million, and today we know it's 2 point something million light years away. The thing is, the longer you wait, two things are going to happen, right? Dark energy is going to do its job. It means that locally, where we are, the local group, the Milky Way, Andromeda, the Triangulum Galaxy, the Magellanic Clouds, and all the galaxies of the local group eventually are going to merge together to make one super galaxy. And we've already named it. We've decided this thing is going to be called Milkdromeda. Great name. But the thing is, all of the other groups in the universe, all of the other galaxy clusters in the universe, they might be bound together to one another, but they're not gravitationally bound to us. So it's like imagining that I've got an infinite ball of dough, and I've got raisins all throughout it. And each raisin is its own individual group. And I have infinity yeast in this bread dough. And over time, the bread is just going to leaven and leaven and leaven and leaven infinitely. The dough is like space, and the raisins are like galaxy groups. And as this dough expands, all the raisins are going to keep moving apart from each other. So if you wait long enough, a few 100 billion years from now, which might be like 10, 20 times the current age of the universe, we won't have any other galaxies to look at. But we'll have new stars in the Milky Way, or in whatever the Milky Way becomes, for trillions or even maybe quadrillions of years. So yeah, we might still have life, but as the universe expands, the nearest galaxy beyond our own local group is going to be farther and farther and farther and farther and farther away. And you won't be able to see it once it gets to a certain point with optical telescopes, because the expansion of the universe will extend its wavelength and stretch it into the infrared, into the microwave, even into the radio. There will come a point, maybe a quadrillion years in the future, where if you wanted to detect the cosmic microwave background, it's not in the microwave anymore, it's in the radio, and you would need a telescope bigger than the diameter of Earth to detect it. If you want to detect these distant galaxies, you would need to know to go look in the radio, because you're not going to find anything in the optical. So you would really need to know what you were looking for. But if you kept looking, if you didn't get discouraged and said, oh, like I went outside and I looked in my own backyard and there wasn't any fruit and I got discouraged, so I came back inside. Like, no, you have no right to expect that the things you're looking for are going to be easy to find. They could be out there. You have to look harder. I feel this way about the far future, whoever's around looking for other galaxies, looking for evidence of the Big Bang. I feel that way today about humanity looking for extraterrestrial life or extraterrestrial intelligence. We have every reason to think it's out there, and we have no idea if it's rare or uncommon or super common. But if we find that it's not super common, we shouldn't get discouraged. Instead, that should inspire us to look harder, because the instant we give up and we say there's nothing out there and it's not worth looking, we're right. And I would hate that. I would hate to shortchange ourselves and our curiosity because we decided it wasn't easy. Let's stop looking. It won't be easy. Don't want to lie to you. For civilization in the far future to find the nature of the universe, the origin of the universe, galaxies beyond our own, evidence of the afterglow of the Big Bang, it will be a Herculean task. And it will be a task that they'll just have to look deeper and deeper and deeper and deeper until they can finally reveal it. And then they'll go, oh my, look at what's out there. But don't stop just because it's not easy.
Excellent. And I think we could say that about just about anything that's worthwhile. We can't ever give up. The next one is from Wes. I've seen a picture from CERN, maybe, showing that one side of the smashed particle disappeared. Could that be dark matter forming from matter collision?
So this is an interesting question, right? We have particle physics experiments like at CERN, at the Large Hadron Collider, where what we do is we take a particle and we take another particle and we bring them up as close to the speed of light as we can, and then we smash them together. And then we see what comes out. And every once in a while, what we do is we basically build detectors around the collision point, and we look for, okay, I'm going to measure all the properties I can of the detritus that comes out of this collision. I'm going to measure each particle, how much energy it carries, how much momentum it has, whether it has an electric charge, whether it has a spin, how it curves in a magnetic field. All these things that we do, all these things that we know to detect the debris of a collision. And then what we do is we reconstruct what happened. Every once in a while, when this happens, we notice that, okay, I reconstructed the collision point and I added up the energy and the momentum of what came out, and there's not enough of it. It doesn't balance. There is missing energy and or missing momentum. What could that mean? Well, the big thing it means is you didn't detect everything that came out of the collision. Why? Could it be dark matter? Well, yeah, but we have other particles that are troublesome to detect, specifically neutrinos. We don't detect neutrinos in particle physics experiments at CERN that do collisions. You can get a rare handful of neutrinos, which is to say, if I had a mole of neutrinos and I shot them through like 100 meters of lead, I would detect some neutrinos. I would stop some neutrinos, right? If I had 10 to the 23 of them. But if I had one neutrino and I wanted to know, okay, I'm going to build a big long cylinder of lead and I'm going to shoot my neutrino through it, how much lead do I need to have about a 50-50 shot of stopping this neutrino? And the answer is about a light year's worth of lead. So if you want to stop a neutrino, you can shoot it at like a neutron star. That's dense enough that it might get a bunch of your neutrinos. But at CERN, no, most of the time we just see missing energy and missing momentum. So if you want to detect dark matter, you need something that either has an energy and momentum combination that rules out a neutrino explanation, that is not consistent with neutrinos, or you need to be extremely precise and say, I know what the neutrino contribution to this is, and I've detected things well enough that I see something extra, this tiny little bump in the data that says it isn't just neutrinos, there's something else. So, at this point, I say, okay, you are going to hear a lot of proverbial boys crying wolf before the actual wolf is there. But don't be discouraged by the fact that someone is crying wolf, and don't say that because they cried wolf and there is no wolf, that means there's no wolf anywhere. Okay? Keep looking, but don't believe the cries of, whoa, there's a dark matter particle that made it right here. And come on, confirmation, people, confirmation.
So we're getting close to the hour mark. So I know there's been a lot of really great questions, but I'm going to show one more question so I don't keep you over, because I respect your time.
Thank you.
You're welcome. So the last question is, could the God particle, Higgs boson, decay into dark matter?
It could. This is something people are looking for. In fact, this is one of the best hopes that the Large Hadron Collider, as it ramps up for its next runs, there are a lot of people who think like, the Large Hadron Collider, it only found the Higgs boson and it didn't find anything else. That means it's a failure. Guess what? Of all the data that the Large Hadron Collider will ever take, it's only taken about 2% of it so far. And that's what's brought us the Higgs boson. So as we collect more data, we're going to say, okay, this percent of the time, I expect the Higgs boson will decay into 2 leptons and 2 anti-leptons. And this percent of the time, it's going to decay into some quarks. And this percent of the time, it's going to decay, right? And so you can go down all the different possibilities and say, what, according to the standard model, should the Higgs boson decay into? And so far, everything has lined up with what the standard model predicts. But all it takes is a small number of detections where either you expect the standard model to do it in a certain way and you don't get those events, or you expect the standard model to do it in a certain way and you get more events than you expect. That could be evidence for dark matter, evidence for some sort of new particle or interaction that takes us beyond the standard model. Because we know the standard model isn't everything. It doesn't have dark matter. It doesn't have dark energy. It doesn't give us more matter than antimatter in the universe, which we clearly have, as evidenced by the fact that, it doesn't annihilate me. It's all matter. Everyone, everywhere, everything is all matter. Even in intergalactic space where you have this galaxy and at the interface, there's no annihilation. Everything is made of matter and not antimatter. Why? Standard model doesn't know. We assume these mysteries have physical solutions, so we have to keep looking. The God particle, the Higgs boson, we have not yet uncovered all of its decays. Same thing for nuclear events, nuclear decays. We've seen events where you get these rare decays where 2 electrons and 2 neutrinos come out of it. What if you get 2 electrons and no neutrinos coming out of it. We've never seen that, but that, if we ever did, that would indicate new physics beyond the standard model. So yeah, it could reveal dark matter, but I'm going to give you the improv answer of yes and, because it could also reveal some fascinating new directions forward for physics that take us well beyond just the dark matter puzzle.
This has opened up so many doors, so many questions, and that's what's so exciting, I think, about physics and about science as a whole. If we close those doors, or we don't even look at the doors themselves, we can't learn and grow. And I'm just so thankful for people like you that are out there looking and exploring and trying to answer these questions that not everybody feels like they can answer. You're out there doing that, and I just love that. Thank you so much for coming back on our show.
Well, it's my pleasure to bring the news to you. And, to everyone out there, if you want to know, hey, what happens if the Large Hadron Collider doesn't find anything new? Are physicists just going to give up? Are they going to stop looking for whatever it is come next? Are they going to stop looking to make greater numbers of collisions at higher energies to see if there's new physics out there? And the answer is maybe. There is a proposal that the entire physics world is unifying together to get behind, to build a future collider that is bigger and more powerful than the Large Hadron Collider at CERN. Currently, it is called the Future Circular Collider. And politics and people who think, what if we don't find anything? Let's not even bother looking. Those mindsets are threatening to kill it. And we're really talking about the rest of the 21st century. Are we going to have high energy particle physics at the cutting edge, or are we not going to have high energy physics at the cutting edge? And so for me, this is a no-brainer. This is a case where, you invest realistically just a few tens of billions of dollars as a civilization, and you get that next step of knowledge. Or you tighten your belt and say, oh, well, think about, like, I could buy 5 fighter jets with that, and then you don't. And then we don't know this at all. So if you care about that, think about advocating for more science in your civilization, right? This is the one thing that the rewards are unknown, but we know exactly what sort of null rewards we're going to get if we don't look.
Absolutely. Absolutely. We all need to stand up and do something. And it's easy by going out and voting. That's very simple. And contacting your congressperson so that they know that science is important for funding, for education. We need to get back into that. So I love that. So for everyone else who's been watching, I want to thank you so much for coming in. We had great communication on the stream tonight. That was awesome. I want to thank Wes, Josh, Phil, Kat, and Jenna behind the scenes that do everything to keep this going. I want you to know on PSF, we have other shows. We have the Secular Soapbox, Women Atheist Unloaded, Sandbox Debates, One Good Reason, and The Bible Says What. If you want to keep on seeing great content like what we had tonight, be sure and like this, share it, subscribe, hit the bell so you can be notified. Join our Patreon account. That's important. Every little bit helps. But for all of us, until we meet again, remember to continue to think critically. Have a great night.